Okay, today we're going to cover biconditional statements. Okay, let me start by writing it in symbols, and then I'll show you how it works. We have P, a double-headed arrow, Q. Okay, now let me show you everything there is to know about that. So here's what it means. I'll move this over a little bit here. Okay, so that's called a biconditional statement. And you'll see why it's called biconditional. Because here's what it means. It means P implies Q and Q implies P. So remember, these are each called conditionals, and it is a conjunction of two conditionals, and that's why it's called a biconditional. Not just the fact that there's two, but it actually that it goes in the two different directions. It's P and Q for both of those, and this conditional is P implying Q, and then this one's Q implying P, the other direction. And you hook those together, you get a biconditional. Okay? Now, in theory, you already know everything there is to know about this because you know about conjunctions and you know about conditionals, and this is just a conjunction of conditionals. But I want to look at it deeper. Okay? So here's what we're going to do. Let me write that in words. Okay? If P, then Q, and if Q, then P. Okay, I'm going to swap those. Because why? Why can I do that? Because the other day we looked at conjunctions and we said that they are commutative. So it doesn't matter what order I put those. So I'm going to swap those. And I'm going to write if Q, then P. And if P, then Q. You don't really have to put those dots before and after the word and. In fact, normally if you're writing a sentence, you wouldn't. I'm just putting them there because not as a grammatical tool or even a logical tool, just as a visual tool. I want in your mind, in your eyes, what your eyes are seeing, I want you to see the two conditionals stand out by themselves. Okay? All right, now we talked about this the other day, that this phrase, if Q, then P, another way of writing that is saying P if Q. Okay, pretty simple. All right. That's like saying this. If it's cold, I'm going to wear a jacket is the same thing as saying I'm going to wear a jacket if it's cold. You see? So, if Q then P is the same thing as saying P if Q. All right? Now, let's look at the other conditional. It says, if P, then Q. The if is connected to the P this time. Okay? So I could certainly write what? I could write Q if P. But I'm going to choose not to this time. I showed you a couple of days ago, or I don't know how many lectures ago, that Another way of writing if P then Q is to say P only if Q. And that's because of the truth table for a conditional. In order for if P then Q to be true, I can't have P be true and Q be false. So P could only be true only if Q is also true. Okay? All right. Now I'm going to take those dots out before and after the word and crunch that together into one continuous sentence. Okay? P if Q and P only if Q. Okay? And let's condense that a little bit more. And we can write P if and only if Q. And there you go. That's what you should say when you see this. You should say P if and only if Q. And we even have a nice little abbreviation for that. Whoops, wrong color. Which is P IFF Q. Okay? That's a biconditional. Now let's look at the truth table for these sorts of things. And the way we're going to make the truth table, because we already know how conditionals work, what their truth tables look like, and we know what the truth tables of conjunctions look like. So what I'm going to do is just use those two pieces of information and make the truth table for this conjunction of conditionals. And that'll tell us the truth table for this. Okay? So let's do that. Okay, there's our two variables, P and Q. Let's write down the 8 possible combinations of truth and falsity for these. This should starting to become second nature for you now. Oh, sorry, not 8. What am I talking about? It's easier than that. There's only 4 possibilities, aren't there? 2 variables, 4 possibilities. Okay, so let's fill in a column for P implies Q. How does that work? An implication is always true unless what? Unless the hypothesis is true and the conclusion is false. That's the only time an implication is false. In all other cases, the implication's true. Okay? Now let's make a column for Q implies P. Now Q is the hypothesis and P is the conclusion. The only time an implication is false is if the hypothesis is true and the conclusion's false. That's the only time an implication's false. All other times, the implication is true. Okay? And now we can use those two to make a column for P if and only if Q, just remembering that this is P implies Q and Q implies P. So it's a conjunction of these two things. How do conjunctions work? A conjunction is true only when both components are true. So that happens here and here. In those two cases, this conjunction is true. In all the other cases, it would be false. So there's our truth table for the biconditional. Look at how biconditionals work. It's true. Here, actually, let me use two different colors. A biconditional is true if the two components have the same truth value. It doesn't matter if they're true or false. The only thing that matters for a biconditional is, do they have the same truth value, either both true or both false. The biconditional is false if the two components have different truth values. That's how biconditionals work. Okay? And now, one more thing, I want to introduce you to the words necessary and sufficient. Okay? So we're going to go back up to something we wrote down earlier. I want to draw your attention. Okay, I'm going to scoot that truth table down. Now, I don't want to get rid of it, but we don't need it anymore. We did it. You do need to know how that truth table works, but we don't need to keep looking at it right now. You want to see it again? You can rewind the video. What I want to do is draw your attention to this line right here. That sentence. P if Q and P only if Q. Okay? All right, now I want to highlight this. P if Q. That means that if Q is true, P has to also be true. So in order for Q to be true, it is necessary that P also be true. So we say P is a necessary condition for Q. Oops, misspelled. Hang on. Okay, that's this. That's P if Q. So in other words, Q implies P. We say P is a necessary condition for Q. And I want you to remember that just about conditionals in the first place. Okay? If you have A implies B, that means B is a necessary condition for A. All right? Now let's look at this one. Okay, so that was coming from, if you remember, if P, then Q. So in other words, P implies Q. But let's look up at the words that I highlighted. It says P only if Q. That means that P can only be true if Q is also true. So in other words, if I know P is true, then I would automatically know that Q must also be true. So it is enough for me to know that P is true in order to figure out that they're both true. So in other words, P is a sufficient condition for Q. All right? And if you put those two together, and you have the biconditional, then you have both of those, and we say P is a necessary and sufficient condition for Q. Okay? And one other quick thing that I want to say before we go. That also means P is logically equivalent to Q. Why is that? Because logically equivalent means that two things have the same truth value, right? When you make the truth table, the columns match. Well, look back at the truth table for P if and only if Q. The only time P if and only if Q is true is on those green rows. Let me in fact erase the other ones. So the only time that P if and only if Q is true is if the truth values for P and Q match. Or here's another way of saying it. Compare this column with this column, and you see that they're the same. So if P, if and only if Q, is true, then the truth value for P matches the truth value for Q. And therefore, P is logically equivalent to Q. Okay? All right, that's it for today.